Okay, hello students, welcome back from the break. I hope you had a good one. So let me continue with lecture 6. This is the second part. We will continue going through the same discussions we pretty much had before, but now we will put them all in the wording of matrix algebra notation that we have just studied. Okay, so in this part we will talk about a few things, including assumptions that we are making when we do OLS estimation of our model and how these assumptions would look in matrix algebra language. Then we will do some couple of derivations and proofs. Okay, so let's go with that. So let me go back. So the first assumption that we already sort of discussed in the beginning of the lecture today is how to write our regression model, right? So in using matrices that we have defined, our vector y is equal to x times beta plus u. And all of these items we have talked about already. Okay, now assumption number one sounds in the following way, that we have a linear in parameters model, right? So exactly as we had before. Now linear applies to the fact that your betas cannot enter in the model in any form other than linear. They cannot be, for example, beta 1 times beta 2 in the model. They cannot be beta 3 square in the model. But this assumption doesn't restrict your x variables to appear in the model in nonlinear fashion. Here's an example. If you have a, for example, production model here, you guys can see this is Cobb-Douglas type production function. If you were to take logs of this, you would have now additive model, right? And in this additive model, then you would see log of labor and log of capital instead of labor and capital that enter your original model. But that is okay. I mean, for Stata, log of L would be just your variable x1, and log of k would be variable x2, and it will see the following linear regression model, which it can easily estimate and give you beta 0, beta 1, and beta 2 estimates. Some more examples you guys can kind of follow here. So you can have x squared in the model, and this will allow you to estimate a parabola sort of, and not a linear relationship, and etc. Okay, so linear in parameters assumption is not preventing us from doing nonlinear functional estimation. The second assumption that we had before, and we will repeat, is that our data are a random sample of n observations, following the population model in the first assumption. Okay, let me give you this slide that I have prepared for you, and let's try to walk through items that I have put on here. So basically, what you guys have is that these are your dependent variables, right? y1, y2, etc. Then there is this block of your independent variables, and then there is, I have written your error terms. Now, what are each one of these items? Like if I take y1, what is the nature of this guy? Okay. Now note, this is not the sample that you would open and you would see the first observation wage is, I don't know, $53 or whatever. That's not when you already have a sample. Before you're sampling, you are wondering what is this representing, and that represents possible outcomes that you would see when you were to knock the first door and ask their wage. So this is a random variable. Each one of these guys is a random variable. And when I stack them together, that's a vector of random variables. Okay, so that's kind of an additional way of looking at it. When I look at these guys, very similarly, each one of these items is a random variable. So this column of the first basically of your x1 is just a column, vector column of many random variables stacked together. Similarly here, your errors, each one is a random variable, so this is a vector of random variables, or a random vector. Okay, so there is a lot in a sense going on here. You have so many random variables that you have to think about. Now, random sampling, what it means, it pretty much says that there are these red lines, or pink lines in my case, right, that separate your observations. And what happens is that when they're independent from each other, in random sampling, information here or random variables here have nothing to do with variables here, have nothing to do with variables here. So basically, across lines, there is no communication, no information spills. Now, you guys might remember, and we will define this later, that this error term, okay, had nothing to do with these guys. Okay, so error term is uncorrelated, as we will see later, with regressors for the basically in the same line. But when I assume this random sampling, what it means is that this random error term has nothing to do with all the other error terms. So there is nothing that puts this together. So these are all pairwise uncorrelated. It also means that this guy has nothing to do with all these guys or these guys. So there is nothing, again, that holds this together with across its own kind of axis or any other axis or any other use, okay? So there is basically all this uncorrelatedness that you can put in or think about when you take each one of these errors at a time. So random sampling makes these lines here, okay? That's the important significance of this assumption. Assumption number 3. This was a pretty kind of technical assumption back then, and it is still here. Back then, if you remember, it just said that not all values of your variable, only variable x that you had back then, were the same. Pretty much what it ruled out, as you already saw in the previous half of the lecture, that x prime x has an inverse. Now we want to restate this assumption for a more general case, and that is exactly this. So whatever dimension you have, if you have 1 or 2 or k variables in your model, okay, this is your matrix x, x prime x, inverse of that has to exist, which means x prime x has to have full column rank. Again, in simple language, that means that there are no columns in x prime x that are basically a repeat of each other, or there is no linear basically relationship between any columns in x prime x, okay, or in x. So all of these columns have to be linearly independent from each other. That rules out situations like when you have a column of ones, which is your 1, you usually do, and if you have one of your variables that is always the same value, for example, everybody has education 10, right? Then you cannot use that variable. That creates a perfect collinearity between education and that column of ones. Cannot have that. Another example, if you have 2 variables, x1 would be, for example, expenditure on food, then another variable is expenditure on non-food. You cannot put another variable that is expenditure in total, because that would be sum of the other 2. That would be collinearity issue, and you cannot invert x prime x in that case. Okay, so again, that basically makes you be careful about what you can use as an x variable in your model and what you cannot. The next assumption, and that's again very important assumption, we have to discuss it well, and I really want you guys to understand well what it means. So it's this zero conditional mean of the error assumption. Now you guys, if you remember, here is basically a slide I want you to look at. Back in time, we just said expectation of u conditional on x is equal to 0. So that's how we phrased it, because we didn't speak any vectors or matrices back then. What we implied was that expectation of any of the error terms for any observation I, conditional, it's basically the x for that I is equal to 0. Okay, so it was basically a scalar kind of expression, expectation of that one random variable, conditional on that one other random variable is equal to 0. Now, given we have now k variables and not 1, a very quick extension would be to come to this line and say, well, now what we can say is that expectation of this one error, okay, for any observation I, given that observation's first variable, second variable, case x variable should be equal to 0. And so we could write this for observation 1, we could write that for observation 2, and all the way for observation n, for any observation that holds. Now, given we have random sample, okay, conditioning on other data would not change anything because these are irrelevant anyway. So if they are known or not known, this will not change. Okay, so in the conditioning here, you can always put in any constants, which again, constant is never changing anything, or you can put in variables that pretty much are independent, irrelevant for this. So one extension that I'm suggesting hence is, because of random sampling, in addition to putting information for that same observation, I can throw in information from all other observations. Anyway, they have nothing to do with this guy's error term. Well, let's put it in. Why am I doing it? Because then, and also we can sort of put this column of ones here, because again, adding constants would not change anything. Then I want to just write this as this matrix X. So I'm now starting to build matrices, basically, into this assumption. Okay, so the assumption now reads as expectation of each one of these errors given the full matrix X, all of the information on independent variables is equal to 0. So we already made that to look like a matrix, okay? Well, as we are basically saying, we can write that for the first observation, for the second observation, and all the way to the last observation, okay? Or, instead of writing it n times, I'm going to package now these guys into vector u. I could just say expectation of a vector u, conditional on x is equal to 0. And now I have written in a very compact way this assumption number 4. Okay? From that assumption, what it follows that expectation of y, and this is vector y, conditional on matrix X is equal to, if we remember how y looks like, right, then if we break this down into two parts, we will have expectation of x beta conditional on x plus expectation of u conditional on x, and we have just assumed that that part is 0. So that simply gives you x beta, because betas are constant, and x we're conditioning on, so it's also viewed as a constant. So basically expectation of your y conditional on x gives you this part. Okay, continuing on. Now here are the important results that we proved in our before matrix algebra life. And I will go through them and show how very quickly you can prove the same things using 1 or 2 lines of matrix algebra. Okay, so back in time, we talked about unbiasedness of OLS estimators. And we basically took B1, then proved that it's unbiased, conditional on X, given assumptions 1 to 4 hold, and then unconditionally it's unbiased as well. Then we approached B0, and I think there was an assignment for you guys to try and prove that it will also be unbiased, okay? So we did this sort of in a long way. Here's a very short, here in one step I am going to derive the same proof, okay? So our B we have written in matrix notation as x prime x minus 1 times x prime y. So this what gives you your formulas, your estimators, okay? And they're stacked. The first one is for B0, the next one for B1, B2, BK. So this is a stack of all these formulas right here. Just like before, we can now insert what y is, and y is x beta plus u. When we open the bracket, what we receive is that x prime x minus 1 and this x prime x cancel out. Okay, and it leads just to beta. Then what we have is x prime x minus 1, x prime u, and that's this term here. here's a quick reminder for you guys. This is something that we already did back then, and this is how it looked like. Basically, after we receive formula for B1, the OLS formula, right? We can insert what yi is, and it's beta 0 plus beta 1 xi plus ui, simple linear regression, right? And once you insert it, we kind of open this bracket and wrote this simplified a little bit. What we received was that this is equal to beta 1 plus stuff. Okay, and this stuff has x's and it has errors in it. We didn't do the next step, but in principle you could similarly write what B0 is. And remember, B0 is mean of y's minus B1 average x. And here again, if you just substitute what y's are, so try to average this, you would receive beta 0, beta 1 average x, and then average u. Remember, attention, this is not 0. Okay, this is sum of all these errors divided by n, not expectation. Okay, this is a finite sum of these guys. All right, so this is your y bar, how it will look like. Then minus b1 x bar, but instead of b1 I can just now substitute this thing. After some simplification you can write it in the following way. Basically b0 is equal to beta 0 plus stuff, and this stuff again has some x's and errors in it. There are two items here, and these two items are sitting exactly here. You see, what is b, which has b0 and b1 in it? It is beta, which has beta 0 and beta 1 in it, plus stuff. And this stuff is made from x's and errors. Okay, and this piece will give you these two formulas, one for basically b1 and the other one for b0, and you guys have both of these stacked right here. Now, once we write b in this form, we can check if indeed expectation of b conditional on x is equal to 0. Let's write how we now represent our b, which is this thing here, right? Then if we open the brackets, expectation of beta just gives you beta. Expectation of all this conditional on x. Expectation passes through all these guys because they are viewed as constants, so they are out, and then it stops right here. Here it is, expectation of u conditional on x. And assumption 4 guarantees that this is 0, which means all of this is 0, which gives you beta. And this is proof for two things, that expectation of b0 is beta 1 and expectation of b1 is beta 1. So both of these proofs are sitting right here in this one line. Okay, that's the power of matrix algebra. Now, it's also easy to see here that if assumption 4 does not hold, that this is equal not to 0 but some to a, for example, a non-zero vector, right? Then when you come here, what you receive is beta plus, and this thing is not 0 anymore. So that's the bias right here. And the larger a is, the larger your bias is. Okay? So the closer this is to 0, the closer assumption 4 is to being satisfied, the smaller your bias, the better your life is. Let's move on. Okay. Now we arrive to the next step. After unbiasedness, we sort of started talking about variances, okay? And variance of OLS, BOLS in particular. But before we derive this variance, we need extra assumptions, one extra assumption, okay? And if you remember, back in time, we made homoscedasticity assumption. And this slide now walks us through what happens, or how we can phrase this assumption in matrix algebra language. Now, let's go back to what we had. So we basically, back in time, were saying variance of any of the errors, okay? Conditional on, again, its own x variable, but now we saw that we can extend this to matrix x because nothing changes, right? So more variables are added, and then random sample allows to put all of the other information on x variables here without any problems. So variance of any of the errors, basically sigma square. Okay, that was our assumption. We want this basically for all n observations. Another assumption that I am going to write now is that covariance between any of the two errors, okay, is equal to 0. And this we sort of already said. When we say random sample, drag this back here, we already said that this has nothing to do with that or that. So these guys are all pairwise uncorrelated. That's basically, here is where I'm going to rewrite it. And then here is what I am showing you, and what it is how variance of your vector of errors will look like, and it's this thing. Let me take one step at a time, and let me give you a couple of rules, okay? So if you guys are looking at a vector, vector z here has two elements, z1 and z2, for simplicity of our life. The way expectation z works is just that expectation goes up here and down here. So expectation of a vector just gives you a vector, where each element here is expectation of the corresponding element in your vector, okay? You can do expectation of a vector, you can do expectation of a matrix. There, expectation would go sit next to each one of the elements of the matrix. So expectation works with a vector or with a matrix. Now, what do we mean when we say variance of z, where z is a vector, okay? Here is the thing. And you guys might remember from basically simpler life, when you just take variance of one variable, that it is equal to expectation of variable squared minus expectation of variable that thing squared, right? This sort of, okay, reproduces this, but now we have vectors, and that is why we have to pay attention to how we do. We cannot just take z square. This is the matrix version of squaring that z.